Welcome back. Not that you went anywhere. Okay, so let's pick off where we dropped off, where we stopped, where we were, what we were doing. We were about to start Worksheet D, and then I realized let's stop and make sure that this is working at all. And I'm glad to say it's working, as you already know. Anyway, Worksheet D, question 1 at first threw me for a loop. I was thinking about it. Why is aluminum hydroxide insoluble in water and sodium hydroxide is very soluble in water? So I sat on that for a second. And then I remembered, we got the solubility rules on the back of our periodic tables last year, and they were just rules that we had to use. But this must be explainable through something. And then I saw it asked me to think about lattice energies, and when I went to lattice energies, I pulled this equation back into my brain. I've left a couple pieces off of that equation. That is the bones of the Coulombic attraction equation. All of the only piece that's missing is the variable, but we're not actually calculating anything. We're not the variable. The only thing that's missing is the constant. There's some constant there. And we just have the variables. Q is the charge, Q is the other charge, R is the distance between the charges. So the charges in these two compounds, we have aluminum that's plus 3. We have hydroxide that's minus 1. So Q1 is plus 3, Q2 is minus 1. And then R is the distance between them. Na is plus 1 and OH is minus 1. And then the distance between them is R. So how are these things different? Well, because plus 3 is a larger charge, it's going to have a stronger attraction to the minus 1. That's one factor. The other factor is the distance. Aluminum and sodium are both on the third period of the periodic table. Our hydroxide's a polyatomic ion. So if you built a hydroxide polyatomic ion, every hydroxide would be the exact same size as every other hydroxide. So it's not the size of the hydroxides that's changing, it's the size of the cation, aluminum and sodium. So if we think about size on the periodic table, as we go from sodium to aluminum, they're all on the third energy level, so they're approximately the same size. But as we go towards the right, we're gaining more and more protons in the nucleus, causing the third energy level to get smaller and smaller and smaller. This means that aluminum is the smaller in size of those two cations. Because it's smaller in size, its center of charge can be closer to the hydroxide. So the R between aluminum and hydroxide is smaller in aluminum hydroxide than the R between sodium and hydroxide. Again, R is the distance between the radius, the distance between the aluminum and the hydroxide, or the sodium and the hydroxide. And if the distance is smaller, think about your math there, when this value here becomes smaller, that makes a larger attraction occur. Because the pieces can be closer together, the attraction would be greater. So not only is aluminum more attracted to hydroxide because of its charge, it's also more attracted to hydroxide because they're closer together. And since it's more attracted, the aluminum is more attracted to the hydroxide. There's a greater pull between them. It's going to be harder to break them apart. Thus, aluminum hydroxide is insoluble in water. Sodium hydroxide is soluble in water. It is more attracted to the water. All right. That was a long answer for number 1. Let's go to number 2. This one's a lot easier. Which solvent, water or carbon tetrachloride, would you choose to dissolve each of the following? So again, water is polar, does hydrogen bonding. Carbon tetrachloride would be nonpolar and doesn't. Pretty much it breaks down to those two categories. Let's look at these here. All of those are pretty much the same answer. CrF2 is nonpolar when you draw its Lewis dot structure. It's a linear drawing in the 1, 2, 3, 4, 5, 6, 7, 8, 1, 2. So it would be an octahedral linear. Octahedral linear. because krypton has 8 valence electrons to start off with, and then you make 2 single bonds. No, it's a trigonal sorry, I was wrong. It would be krypton 1, 2, 3, 4, 5, 6, 7, 8, and then there'd be 2 bonds, so it's got 3 pairs. Yeah, it's a trigonal biplanar linear. Sorry about that. It's a trigonal biplanar linear. So if it's trigonal biplanar linear, it's nonpolar and more likely to dissolve in the carbon tetrachloride. Carbon dioxide's simple nonpolar, it's going to CCl4, and then that one at the bottom, that's a nonpolar ethene, it's a double bond, ethene. 2 carbons, eth, change the ending to ene from ane. Again, nomenclature not important. SF2 is polar, it's bent. SO2, ooh, this one a lot of people can draw wrong. Let's just draw it. Sulfur has 1, 2, 3, 4, 5, 6. It's going to double bond to an oxygen. It's going to double bond to an oxygen. And then there's this extra pair of electrons. And so it's a polar molecule. It's a trigonal planar bent. Trigonal planar, because it's in 1, 2, 3 directions. But it's actually bent because it's got that pair of electrons instead of bonds. So it's trigonal planar bent, and that means it will dissolve better in the water since water is also bent and it's got a dipole. Here we have already talked about formaldehyde a couple times. And then MgF2 is an ionic compound. It should dissolve pretty readily in water since water is polar and has a center of positive and negative charge. Similar questions here. Which one would be more soluble in water? You think about hydrogen bonding, you think about polarity. I'm just going to read the answers real fast to give you time. NH3 has hydrogen bonding, so it would be more soluble. pH3 would be polar, but it wouldn't have hydrogen bonding. So, NH3. Let's see, in B, the CH3 is completely nonpolar, so it probably wouldn't dissolve in the water well at all, whereas the other one at least has that weird little polar CN thing going on. That's cyanide. And then in C, we've got this thing down here that's got the OH coming off the end over there, and that OH hydroxide allows it to do hydrogen bonding. Number 4 here. So each of these molecules, if we want to just kind of zoom in there for a second, let me figure out a way to zoom in. There we go. Each of these molecules is got the hydroxide coming off of it, right? They've all got the hydroxide on that one side, but then they've got this like chain of carbons and hydrogens. And look, that's what we were talking about earlier. Look, that means there's a CH2 next to another CH2, next to another CH2, next to another CH2, in a whole long line. And since they've all got that one hydroxide on the end of the tail, that hydroxide can be considered to be an equivalent issue with all of them. So it's not the hydroxide that we're concerned with, it's the rest of the molecule. And as we go down here, we kind of get a sense of that nomenclature thing we were talking about. Let's pause. All right, here's your 30-second nomenclature introduction. 1 carbon, meth. Whoa, that's not what I meant to do. So 1 carbon is meth, 2 carbons is eth, 3 carbons is prop, 4 carbons is bute, and then they make it easy. Penta 5, hexa 6, hepta 7. Guess what 8 would be? Yep, octa. Very good. And then since they've got these hydroxides on the end, they went from methane to methanol and from ethane to ethanol. So they changed the ending to ANOL to represent that there's hydroxides coming off the tail. That heptanol, though, that's got a long carbon chain, doesn't it? So the longer the molecule is, the more of those CH2s that are attached, the less and less soluble it's going to be in water, because each of those CH3s and CH2s are non-polar pieces that aren't attracted to the water, which is why we see the solubility dropping very drastically as they add more CH2s. Okay, so the last worksheet, I don't know if you remember, I said that we chopped a whole lot out of the last chapter. We've got some terms here. You put a solute into a solvent, it changes the properties of the solvent. We call that change colligative properties. Common colligative properties are freezing point depression, boiling point elevation, and lowering the vapor pressure. We really only talked about that last one, the vapor pressure, with Raoult's law. But in any case, changing the freezing point, changing the boiling point, or changing the vapor pressure, if you add more solute, you cause the change to increase. If you add more solute to your water, you're going to increase the boiling point, change the freezing point to even lower, or lower the vapor pressure even more. Basically, when the solute impacts how the solvent acts. Notice I've got the answers, but then I crossed it off because while this is interesting stuff, we're actually going to come back to this later in the year, and you don't need to know about boiling point elevation, freezing point depression yet. Again, number 12, we don't need to know about freezing point depression yet. Although I do like this little story about World War II and antifreeze, because antifreeze does two things. It doesn't just stop your radiator from freezing, it also stops your radiator from boiling over. It does both. So that's pretty cool. This is the end, or last worksheet. Hope you guys learned a lot today. Sorry I couldn't be there. And go to YouTube if you ever want to watch these again or maybe take a nap.